Today we're going to start Chapter 15, Properties of Sound. I'd like you to demonstrate knowledge of the nature of sound waves and the properties they share with other waves, and then solve problems relating wavelength, frequency, and speed of sound. So a similar equation to what you've done, now we're going to do it with sound waves. So 15.1, Properties of Sound. A sound wave is made up of, or it's a longitudinal wave rather than a transverse wave, made up with compressions and rarefactions. Now the compressions are regions of high pressure, so the wave gets kind of squished or compressed, and the rarefactions are areas of low pressure where they get drawn out or spread out a bit. These waves, just like any other wave, are characterized by speed, velocity, frequency, wavelength, and amplitude. So you have the same type of properties as you would any other wave. These types of waves can also undergo reflection, refraction, diffraction, and interference. So whether we're talking about light waves or sound waves, you've got similar properties. They will reflect off of other objects. They will bend when you go into a new medium. Diffraction, they'll bend around corners. You can hear sound around walls, not just in the straight lines. And sound waves can interfere with each other. You can have constructive where it gets louder, or destructive where it doesn't, or cancels out. And they move through the air because some vibrating source, which is required to make sound, produces regular variations in the air pressure. So in order to hear sound, you need something vibrating. If you go ahead and put your fingers on your vocal cords and then just talk whatever you want to say, maybe read the definition of sound waves, you can notice that your throat is vibrating. And that vibration causes the air around it to compress and spread out, and that sound travels through the medium of air and eventually gets to our ears where we can hear it. So the easiest way of thinking of waves is longitudinal. This is what we've talked about before. If you're dealing with compression waves, every time you have a high region or a crest like here, that's where the wave will be compressed. And the trough, or the low pressure regions, are where it kind of spreads out. And then it compresses again, and there's your rarefaction. It compresses again at the high point and then spreads out. So you've got regions of compressions right there, the black lines, which correspond with your high pressure regions, the crest parts, and you have regions of rarefactions that would represent your low pressure regions, kind of like your troughs. So the air molecules get compressed and spread out as they move through the air, the medium. You really should read page 350, and it kind of talks about how this compression and rarefaction goes with a really nice excuse me, diagram on that page. Now the speed of sound depends on temperature. At sea level and 20 degrees Celsius, the speed of sound is 343 meters per second. So V sub s, the velocity or speed of sound, is 343 meters per second. Notice this is at 20 degrees Celsius because the warmer it gets, the faster the air can move, and therefore the sound can travel faster from the source to the detector. So you have to keep in mind with any speed of sound problems, you need to look at the temperature. We know it increases. This is how much it increases. The speed of sound increases 0.6 meters per second for every 1 degree Celsius increase in temperature. So if you're going from 20 to 21, the speed of sound isn't 343, it's now 343.6 meters per second. If you have a 10 Celsius degree change in temperature, if you're at 30 degrees, well, 10 times 0.6 is 6. You need to add that to your original 343, and therefore the speed of sound at 30 degrees would be 349 meters per second. It does the same if you go colder. If it gets colder, it's going to slow down by the same amount. And the speed of sound is also greater in solids and liquids than in gases. Now the main reason for that would be the medium is closer together, so the sound can bump into the next particle quicker than it would in a gas. I grew up with cowboys and Indians. I know that's not politically correct, but back in the day when you watched the westerns, the Indians would listen to the ground, put their ear on the ground close to the railroad track to see how close the train was going to come, because the sound would travel faster through the rails than it would through the air. Just like before, since this is a wave, the speed is related to, or related by, the wavelength and the frequency. So your velocity, your speed of the wave, equals the wavelength measured in meters times your frequency measured in hertz, or 1 per second. So if this is wavelength and this is hertz, which is the same thing as 1 over seconds. Sorry, we know the wavelength measured in meters. If you take a meter times a 1 over seconds, you get meters per second, which are units of velocity. So let's try a simple problem here. A sound has a frequency of 216 hertz. What is its wavelength? Well, we know velocity relates wavelength to frequency. And if we're at 20 degrees, the velocity of all sound waves is 343 meters per second. The wavelength we don't know. The frequency is 216 hertz. So if you divide both sides by 216 hertz, or 1 over seconds, we end up getting a wavelength of, I assume you have the answer by now. I will double check on my calculator. 1.59 meters. If we did the same thing, had the exact same tuning fork, something that's making sound at 216 hertz, but this time the room is 40 degrees Celsius, what is the wavelength? Well, the equation is the same. We don't know the wavelength. The frequency is still 216 hertz. But now the speed is not 343. To go from 40 degrees to 20 degrees, we're looking at a 20 degree Celsius degree change in temperature. So if my change in temperature is 20 Celsius degrees, and the temperature, or the speed, changes 0.6 meters per second for every 1 Celsius degree change in temperature, it looks like our speed is going to increase by 12 meters per second. So instead of 343 like we normally have, it has to be 12 higher than that, 355, because it's a warmer temperature. So if we take our 355 divided by 216, you end up getting a wavelength of 1.64 meters. So the wave is going to stretch out just because it's going faster. The frequency doesn't change. That's produced by the source that's making the wave. So the wavelength has to compensate for that extra speed. And that's the end of the first half of section 15.1.